Okay, we're going to talk about operational amplifier, simply called op-amp. Okay, operational amplifier, it's an active circuit element. It's an active element. So what is an active element? It can able to supply power to the circuit called active element. Passive elements are window resistor, capacitor, inductors. Those are passive elements. But operational amplifier, active element. It acts like a dependent source, a current dependent current source, voltage dependent voltage source, something like that. It can sum, amplify, integrate, or differentiate signals. So it can sum two signals or amplify two signals, or differentiate two signals. It can also perform mathematical operations like addition, subtraction, multiplication, and division. Okay, here is a symbol for operational amplifier. There are two input terminals. The two input terminals we indicate with V1 and V2. Okay, V1 is called this is inverting input pin, this is non-inverting input pin. So there are two input pins, non-inverting and inverting. Okay, inverting is nothing but the output is going to be inverted 180 degrees. So for example, if I give this as an input to inverting pin, my output is going to be inverted 180 degrees. So it's opposite. Okay, non-inverting, it's not going to invert the output is going to be the same. Okay, and so two input pins, one is inverting pin, another one is non-inverting pin. The third pin is output pin, and there are two more pins. Those are called positive power supply and negative power supply. Here is the positive power supply, V plus, and negative power supply, V minus. These are the 5 important pins for the operational amplifier. In reality, most of the operational amplifiers are available on IC chip, integrated circuit chip. There usually you'll see 8 pins. Some of the pins we will use them, some of them are they're not going to connect anything. Okay, so that's about basics of operational amplifier. Okay, here is the equivalent circuit of an operational amplifier. Here A is called open loop voltage gain. Okay, A is called open loop voltage gain. That open loop voltage gain, in ideal case, that value is infinite. So ideal case, practical case, operational amplifier, there is not big difference in the output for the ideal case and practical case. So for time being, I'm going to go with ideal operational amplifier. So the important point, ideal operational amplifier, this VD is differential input voltage. This value is always 0. Okay, so that's one of the important point. This voltage is 0. It's basically virtual voltage difference. That means if I have, say, V2 equal to 10 volt, automatically V1 is going to be 10 volt. Okay, so what I meant to say at the end of the day, here for operational amplifier, we always take V1 equal to V2 no matter what. This is one of the important point you need to remember for operational amplifier. Now the second one you need to remember, the input resistance here is infinite. Since it's infinite resistance, currents going in or currents going out, that is always 0 ampere. Okay, currents going into the operational amplifier is always 0. These two are the important points for the operational amplifier. I mean, whenever you're solving examples, these two comes into the picture all the time. Another important point is the output resistance of operational amplifier is equal to 0. So there is no resistance here. Output resistance at this point is 0. Now, another important point, the voltage gain can be any number like 100, 1000. Okay, say I give a 10 volt source here. Okay, I'm giving a 10 volt source, and say it has a gain of 10. So gain is nothing but output over input. output over input. So what is my output in this case? If I give input as 10 volts, output should be 100 volt, right? As gain is 10 and input voltage is 10, my output should be 100. But the output is going to be limited, or it's going to cut off at this supply value. So if supply value is 15 volt, the output, it can give you maximum 15 volt, even though the gain is 100 times more or 10 times more. Okay, so output is going to limit at the positive and negative power supply. Those are the three important points. What are the important points? First thing, V1 equal to V2 all the time, and currents going in always. Okay, and the third one is output value is never going to be more than supply value. So those are the three important points. V1 equal to V2, and current going into the operational amplifier is 0, and supply voltage limited to source, output voltage limited to the supply voltage. So the next topic is inverting amplifier. Inverting amplifier. Sorry about my writing there. So the inverting amplifier is nothing but you are giving your input to the inverting terminal. Remember, this negative terminal is inverting terminal. That value, the voltage here is V1. This is non-inverting terminal, or V2. Whenever we are connecting our input to this negative terminal, we call that as inverting amplifier. So as I mentioned, inverting amplifier, what it will do, if you give input value sinusoidal like this, it is going to be inverted like this. Okay, it's going to be out of phase 180 degrees. That's inverting amplifier. Now in this inverting amplifier, here he's asking us to find V0. Okay, we always know V1 equal to V2. So in this case, V2 is grounded. So can I say V2 equal to 0? So V1 equal to V2 equal to 0. So the voltage at this point is 0 volts. Now I'm applying KCL at V1. If I apply KCL at V1, here is the current going here. I'm taking that as I1. Current going there, I'm taking that as R2. And this resistance is R2. Current going through the R2 is I2. And I'm taking this resistance as R1. Current going through it is I1. Sometimes you might see this R2 as RF. F is nothing but feedback resistor. Sometimes we represent that R2 as RF. Okay. Now, so if I apply KCL at V1, I know the current going here is 0 amperes. So I1 plus I1 going out, I2 is also going out, equal to 0. I1, can I write this as V1 minus V source divided by R1. V1 minus V source divided by R1, plus I2 is nothing but V1 minus voltage at this point is V0. V1 minus V0 over R2 equal to 0. Okay. After simplifying this, it will end up with minus Vs over R1 equal to V0 over R2. So if we simplify this, V0 equal to minus R2 over R1 times Vs. Okay, so this is our output value. Okay, now say if R2 equal to 100k, R1 equal to 10k. So if R2 equal to 100k, R1 equal to 10k, so V0 is almost inverted. I mean, it's all inverted, but 10 times larger than the source value. Now assume the source value is 10 volts. What will be the output value? Minus 100 volts. As I mentioned in the previous case, now if I have this positive power supply, most of the cases this positive power supply and negative power supply is limited to 15 volt. Okay, so even though I'm supposed to get 100 volt, if I take Vs equal to 10 volt, Vs maximum, the output voltage is going to cut off at 15 volt, because even though it's supposed to give you 10 times the input value, which is minus 100 volt, but output is going to cut off at the source voltage. The next one is non-inverting amplifier. Non-inverting amplifier is nothing but we are giving input to the non-inverting terminal. So here this is non-inverting terminal. I'm giving input to the non-inverting terminal. So that's called non-inverting amplifier. Now can I say my V2 is, we know always V1 equal to V2. In this case V2 is same as Vs. Okay, now at V1 apply KCL. If I apply KCL, I'm taking I1 is going in this direction, I2 is going out. So V1 minus 0. So if I apply KCL at here, V1 minus 0 over R1 plus V1 minus V0 over R2 equal to 0. Okay, so if I simplify this, I will end up with V1 over R1 plus V1 over R2 equal to V0 over R2. Now I need V0. So if I further simplify this, I'm going to write it down here. V0 equal to, I need to take R2 to the other side. When I take it to the other side, it's V1 times 1 plus R2 over R1. Okay, now I already know V1 equal to V2, which equal to V source. So V0 equal to V source times 1 plus R2 over R1. This is the output value for non-inverting amplifier. Okay, I will stop it here in this video. I'll continue with the next video. Thank you.